This is from IMO 1968, question 1. You ask prove that there's only one and only one triangle whose side length is consecutive integer and one of those angles is twice as large as the other. How to prove that? Let's say that this is a triangle called A, B, and C. Those side lengths are consecutive integer. Let's say it is n minus 1, n, and n plus 1. And one of those angles is twice as large as the other. Now we know that if the length is smaller, the angle also smaller. So in this case, the angle A is less than the angle B, less than the angle C. So we can have only three possible cases. That is, double of A equals to B, or double of A equals to C, or double of B equals to C. Then we'll consider each of the cases later on. So we're going to apply cosine rule and sine rule for this question. So we start with cosine rule and we go to the angle A here. N minus 1 square equals to n square plus n plus 1 square minus 2 of n plus 1 cosine A. And this means that cosine A is equals to n square plus n plus 1 square minus n minus 1 square over 2n plus 1. This is x square minus y square. So you have x plus y, x minus y. And we have 4n. So this is n square plus 4n over 2n plus 1. That is n plus 4 over 2n plus 1. Likewise, we can get sine B will be equals to n minus 1 square plus n plus 1 square minus n square over 2 of n minus 1 plus 1. And this will give me n square, and n cancel off, and there's a 2. So this will be 2 of n square minus 1. We don't have to find the cosine C for some reason that you will see later. Next, you look at sine rule. N minus 1 over sine A equals to n over sine B equals to n plus 1 over sine C. And we need to consider each of the case here. Case 1, 2a equals to b. If 2a equals to b, we look at this. Then this will be n minus 1 over sine A, n over sine B. B equals to 2a, so this will be 2 sine A cos A. So cancel the sine A. Cosine A is equals to n over 2n minus 1. But cosine A itself equals to n plus 4 over 2 of n plus 1. So we have to solve this equation. Cancel the 2. So this is n square plus n equals to n square plus 3n minus 4. So this will mean that n square cancel off, 2n equals to 4, n equals to 2. Now it looks good to get the answer here. However, n minus 1 and n plus 1 come from the side length of triangle. From the triangle inequality, we know that the longest, that is n plus 1, must be less than, strictly less than, the sum for the other two. And this means that n must be at least equals to 2. So we have to reject it, otherwise it can't form a triangle. So we can't get anything from case 1. How about case 2? 2a equals to c. Then we'll consider this 2. You see that everything is almost the same. N minus 1 over sine A equals to n plus 1 over 2 sine A cosine A. So cancel the sine A. cosine A equals to n plus 1 over 2 of n minus 1. Cosine A is equals to n plus 4 over 2 of n plus 1. And this means that, cancel the 2, n squared plus 2n plus 1 equals to n squared plus 3n minus 4. And therefore, in this case, n is equal to 5. Congratulations, you get one answer. So we have to see whether is there any answer from C equals to 2b. So let's continue for case 3. So we look at this two, n over sine b equals to n plus 1 over C equals to 2b. So 2 sine b cosine b. Cancel the sine b. Sine b is equals to n plus 1 over 2n, and cosine b is equals to n squared plus 2 over 2 of n squared minus 1. So again, cancel the 2. This look a little bit complicated. You have n cubed plus n squared minus n minus 1 equals to n cubed plus 2n. Maybe continue here. This will have n squared minus 3n minus 1 equals to 0. So in this case, n will equal to 3 plus minus square root of 13 over 2. And this is not an integer, so we do not get any answer from case 3. So with this cosine rule and sine rule, we can solve this question from IMO 1968. This end of the lesson. See you again. Bye bye.